was recording. Just had to change the recording settings. So then after OT, programmable logic controllers, PLCs, these are the main computers that control industrial processes. So they don't look like a normal computer, like you and I would expect. So they're way more rugged and durable. They don't have a lot of extra peripherals. It's usually just relays. Instead of like digital I/O, it's usually just relays. And then some sort of CPU, some memory, and maybe some extra components, so like a network module. They're pretty bare bones, and they're quite different from a normal computer. Remote terminal units are very similar to PLCs, so they're also smaller, more durable computers. They don't have as much control capabilities as PLCs do, so they don't have the same level of processing capabilities. So they mainly just collect and correlate the data. HMIs are just a visual interface. So it's some workstation that a human operator can use to supervise and monitor some industrial process. So it can report the state of things. So like if the water level is getting low in some water tank, it'll report that. And it's usually visual. Like you may have a nice visual diagram for that. A data historian collects and stores data about processes, sensor readings, input outputs, and it usually just stores it in a database. And then sensors are actuators. Those are basically what interact with the physical world. They're how we monitor, like how we gather information from the physical environment. So pressure sensors can gauge what the pressure of a given tank is. Motors can be used to like move things on a belt, stuff like that. So those are kind of the main components that make up an ICS system. And so this is a really good diagram that indicates how these components work together. So when I was talking about the IT versus OT network, the IT network is in that blue square over here. So this is all the corporate IT. So you've got engineering workstations, you've got laptops, you've got servers. And this may be fully segmented from the OT network, or it may be somewhat interconnected. That's kind of on a case-by-case basis. Then the OT network would be all of this. So it would be the green and red box. So it would include both the supervision network and the production network. So we talked about SCADA and how it's mainly used for supervision and relaying commands. So you have these supervision consoles that allow a human operator to send commands to things like the PLC. So the SCADA network, there's no autonomous sending of commands. It has to be initiated by a human operator here. And then the data historian, it's just storing that data, which it gets back from the RTUs and the PLC. And so it'll just store that in a database. Maintenance laptops, so like if something needs to be maintained, Some engineer can bring their laptop in, plug it in, maybe send commands to the PLC for like a firmware update or something like that. Then we talked about the RTUs, the PLC. The PLCs interacting with some external components. So like here we have like a light, and then I can't quite tell what this is, maybe a spigot or something. And then you have some more PLCs here interacting with more components. And this, I assume, is an HMI. It's not labeled, but that's kind of like a broad overview of how things connect. This is just one example of a test ICS network. This is another one. So this one was provided by FireEye. So this one is more what you want to see, specifically because they have some sort of controls in place to secure their ICS components by segmenting their IT and OT networks. So you can see that by these firewall symbols. So they have their IT network, and then they have a demilitarized zone. So I don't know how much John has maybe touched on that, but basically this is just a way, like this is just a control. So that way, like when you're setting up a network, you're not having like IT and OT directly connected. So you have this demilitarized zone. So like things from OT, if it has to be communicated back up, will communicate back up to the DMC, and IT, same thing. So it's just a matter of routing. It's a little bit safer than directly connecting things. Like if this was gone, then IT and OT could potentially be directly connected and just have some sort of, like they could be plugged into the same switch or something, and that could potentially be a problem. So then we talked about distributed control systems, so that DCS. So here we have different engineering workstations and PLCs, and then sensors and actuators. And those also are communicating with SIS controllers, which are monitoring to see if it's staying in a safe state. And then if it's getting into a dangerous state, it will actually try and bring the physical process back into a safe state by potentially changing values for like motors, actuators, stuff like that. And that's all based on predefined control process information that has to be supplied by the users when they're first setting up their process, their industrial process. So before I begin, before I continue, are there any questions on kind of the components in ICS?
Real quick, do you think you could go back to the slide of the terminology? Just take a quick screenshot.
Yeah. And I'll also share these slides after. So if you want to refer back, you'll be able to do so.
Thanks.
So now I want to talk about how PLCs are programmed. So the logic behind PLCs is very different than what we would use to program, let's say, a microcontroller. So industrial control processes originally used something called relay logic. And so they had these big relay panels that they used to control the processes. So these were multiple electromechanical relays that were physically wired together to perform a certain function. And the relays could either be on or off. And the opening and closing of these relay contacts basically controlled whether they're on or off. And whatever the relays were connected to would then be either on or off. So you could chain the relays with things like switches and relay coils to create more complex control flow. So relay coils basically, I don't want to misspeak because I'm not exactly sure how they were used in relay logic, but typically relay coils only can represent 1 bit of information. So you can think of it like binary, like 1 or 0, so on or off. And switches are pretty similar. And it's really not used, like this type of logic is really not used much anymore because of the number of electromechanical components and how much wear and tear would be put on those components, and then the cost of replacing them. It just wasn't efficient representing complex processes and then controlling them over long periods of time. So relay logic eventually got replaced by ladder logic. And ladder logic uses a lot of the same concepts, but it's a little bit more of a shift towards digital representation. So it supports a lot more functionality than relay logic used to. And you're actually, instead of physically wiring these components, you're representing the components with digital symbols, and then you're programming. So you're compiling a program and then flashing it to the PLC. So it's kind of a weird combination of relay logic and then traditional programming. So it can support a lot of different operations. Like it can support Boolean logic, which relay logic could do. But ladder logic can also do timing. It can do counting. It can do comparisons. It can do basic mathematical functions. And it can do special functions. So it can do things like it can use shift registers. It can communicate for like different protocols. So this is much more complex than relay logic. And so a typical ladder logic diagram would look like this. So these are the same diagram, just different labeling. So you've got a positive and a negative rail in a ladder logic diagram. And the positive is indicated by the green and the negative with the red. So you can think of it as power and ground, usually. And then you've got a lot of different components here. So you've got, like with this PB, that stands for a push button. So that's a physical button that you can push, and it'll connect this wire to this rail, essentially. And same with this one, this push button. If it's pushed, it connects it to that rail, power goes through. You've got the L is for a light, I believe. M is for motor. The C's are for contacts and like contact relays. And then specifically, you can see like in the left hand, they're actually labeling like inputs and outputs for your convenience, whereas the right one doesn't. So these obviously are outputs, and then these are all inputs. And then like a push button would obviously only have two states. It can only be on or off. So it can only be pushed or not pushed. Same with most relays. So those can only really represent one bit of information. But there are registers that can represent more than one bit of information. So you have the ability to manipulate memory using those registers like you would in normal programming. But yeah, this is pretty different from how you would write code for a microcontroller, because you're not using words, you're actually diagramming it out. And it definitely takes a lot of getting used to. So we have a ladder logic exercise where we actually make a ladder logic program, but we'll save that towards the end. Okay, what's going on here? Can you still see the slides?
Yeah, you were on communications protocol slide.
Yeah. Okay, yep. All right, so ICS devices usually communicate over serial protocols, but there's been a recent shift to various internet protocols as well, so that's been in more recent years. Some of the more common ones that you might see when working with ICS systems are Modbus RTU, which is a serial version of Modbus, Modbus TCP, DNP3, S7, Profinet, BACnet, ICCP, Niagara Fox, and C37. So you may see some of those. There's tons more. A lot of ICS protocols are proprietary. So if you're working with some PLC, chances are you're going to encounter a proprietary language, and you will most likely have to reverse engineer it because you won't find documentation for it. So that's one of the major obstacles for pen testing ICS systems, is there's a huge amount of effort spent reverse engineering and documenting some of these proprietary protocols. So one of the most common and most used ICS protocols is Modbus. And that's because it's been around for a while and it's easy to use and it's non-proprietary. Those are kind of like the most, well, those are the reasons why it's one of the most used. So it's the Modbus RTU version is a serial communication protocol, and it was developed in the 1980s. It uses a master-slave setup. So the master pulls slaves to get state information and to get like the packets back. Only 247 slaves per master because Modbus addresses are 8 bits. Then Modbus TCP. I have a comparison on the right of Modbus RTU and Modbus TCP. So Modbus RTU, because it's master slave, a Modbus RTU message has to include the slave ID. So it'll have the slave ID, it'll have the function code, and it'll have any data that needs to be sent. Modbus TCP is a little bit more complex. So it has the data and the function code as well, but it also has information like the transaction ID, the protocol ID, the length of the header and unit ID. Some common Modbus functions are like read and writing to coils. And so coils represent a single bit of information. So you can kind of think of it as like a single bit register or a Boolean, if that makes it easier for you. Then you can also read and write to registers, so those hold more than one bit of information. And you can also read and write to multiple registers at the same time. Modbus TCP communicates over port 502. It does not authenticate. So there's no sort of authentication mechanism for Modbus. So any person can set up a Modbus client and communicate. So it'll accept anyone's messages and believe it to be valid. So that's a major, major issue with Modbus as a communication protocol. And you'll find that's very common for ICS protocols. Authentication is very rare for ICS protocols because, first and foremost, ICS is concerned about availability. They want their systems to be up and running for as much time as humanly possible. They don't want those systems going down. They don't want communication to take a long time between different components. So, like, let's say a sensor updates its state, and you want to have that, you want to be notified every 15 milliseconds. I'm completely making up this scenario. Well, if you have an authentication mechanism, suddenly you're adding either a lot more length to a packet or you're adding multiple more packets to the protocol, to the back and forth sequence, basically, in order to authenticate. And so that slows down that communication substantially, and you can no longer get that information as quickly. You can't get that accurate 15 millisecond state update from your sensor. You can't communicate that back, like, from the PLC to your engineering workstation or your HMI that you're using to monitor the process. Suddenly you've got 30 millisecond delay or 40 millisecond delay. And while that seems very small, in an industrial control system, that delay is often unacceptable. So that's one of the reasons why authentication is not a high priority. And you'll see that security was often neglected for availability in a lot of the design decisions in both the communication protocols and in the design of PLCs. So this is another hands-on exercise. Oh, I see we have something in the chat. Sorry, for whatever reason, whenever I'm presenting, my Zoom chat does not pop up. Like, I click it and it just doesn't pop up. So I have to actually stop presenting to see it. So if you don't—
I was going to ask if there's like any other application specific authentication that goes on, or if there's just none at all.
So it definitely depends on the protocol. I think there's a couple that do have authentication. A lot of the times they try and use segmentation and firewalls and other security measures, so that way they don't have to apply authentication in the protocol itself. They can just assume that anyone who can access that PLC, anyone who is on that same network, is supposed to be there. And usually that's a fair assumption if you have proper segmentation of your IT and OT networks, and you have proper firewalling, you have good alarms. But if you have an insider, then that falls apart. Then if you have an insider threat, some disgruntled employee could send bad data, and the PLC would be like, all right, yep, that's fine. We'll crash everything. So I know that's not a direct answer to your question. As far as application-specific authentication methods, I don't think so. Like, pretty much the communication would be baked into either the communication protocol or like any sort of administration of the PLC. So it may protect against reading or writing to the PLC directly. But that's kind of the best answer I can give without doing more research. Does that help answer your question, or not really?
Yeah, no, I get it now. The part about the firewall was helpful.
Mm-hmm.
Thank you.
And we'll talk more about various mitigations and what companies can do to kind of protect their ICS systems in a later slide. All right, let's get back to the presentation. All right, so we've already touched on a couple of these, but here are some of the most common ICS vulnerabilities. So we talked about how there's no authentication in most communication protocols for ICS. Also, very little information is encrypted in communication protocols for ICS. So the communication protocols I'm familiar with, everything is exchanged in clear text. So if an attacker wanted, they could just sit on the network and just capture that traffic and read everything. So that's another problem with communication protocols for ICS. But once again, you get in that trade-off between security and availability, because if you start adding encryption, you start taking a lot of time to encrypt, and you may run into errors with the encryption and decryption process. So that's one reason why you don't see encryption being used in a lot of these communication protocols. On the PLC itself, oftentimes the firmware is outdated. Either it hasn't been updated, or the company actually hasn't issued security patches or firmware updates for the PLC to address critical vulnerabilities. They just kind of let it be. So you'll often see the combination of the two, both the manufacturer and the users both neglecting updating in some form or another. So that can be a major issue. You can get remote code execution, stuff like that. IT and OT networks not being segmented properly, that's a huge one. That one leads to compromise a lot. So if it's either not there or it's just not segmented properly, that can easily result in your OT network getting compromised, and then your PLC being taken over, an attacker shutting things down or doing whatever they want. Replay attacks. So because there's no authentication or encryption, an attacker can capture some packets from the exchange between the PLC and a workstation or an HMI, and then they can replay it later, and make the PLC think that it's actually talking to the HMI. The PLC may have ports exposed directly to the internet. So with these new internet protocols, so like Modbus TCP, these ports get exposed often directly to the internet. And that means anyone can send commands to the PLC. And that is a huge issue. Unless the company takes really, really good care to discard any attempts to write to the PLC through various measures, that could be a major issue. So as a pen tester, trying to pen test an ICS network, you have a couple steps that you usually want to take. So like this is a rough game plan for pen testing an ICS network. So first and foremost, you're going to do your recon. That's never going to change. You're always going to have to do recon. Specifically, you want to know what the network topology is. You need to know what sort of ICS components you're dealing with. Like, are you dealing with a distributed control system? Like, do you have some PLCs on there? What kind of PLCs do you have? What communication protocols are they using? Is the IT and OT network properly segmented? Are there safeguards that the company is using against attack? So specifically, when I say safeguards, I'm thinking about like the SIS. So do they have something that's monitoring the state of the industrial process, and then if it gets into an undesirable state, it reverts it? Are there any alarms set up? So similar to like logging software or taps used in an IT environment, there are similar things for an OT environment. So they can configure alarms, like if someone tries to write to a register or write to a coil, an alarm could be triggered, and then an operator would be immediately notified that, oh, hey, we may have an attacker in the system because someone just tried to write to this. The PLC is not expecting anyone to write to it right now. You could have alarms set up where if it exceeds a certain pressure, it'll automatically revert back to another pressure and it'll trigger an alarm. Things like that. So knowing those safeguards is very important. And also knowing what communicates directly to the PLC. So depending on what you want to do here, you may want to try and communicate to the PLC. And if you want to do that, you need to know how it expects to receive input. So you need to know what is currently communicating with it. And you need to either take control of that or you need to masquerade as it. So that's your basic recon. After that, you'll do your port scanning, try and see if you can find any open ports associated with common ICS protocols. And when I say scan the target, I'm usually referring to engineering workstations or HMIs. So those are usually the most likely to be connected to PLCs, and they're usually juicy targets. But if the PLC itself is actually reporting open ports, then that's even better. You can communicate directly to it if you are finding that it has an open port. Then enumeration, so trying to find usernames, control groups, machines. In all of these steps, I should preface, all these steps will differ depending on the network topology and how they have the IT and OT networks segmented. So if they have them firmly air-gapped, then it's going to be much, much harder for you. But if the IT and OT networks have a lot of overlap, then your job as a pen tester is much easier. So if you're not already in that OT network, you want to try and pivot to it. So if it's air-gapped, you're going to have to find a way to defeat that. So one way is to sneaker net. So that just means using some sort of physical data transfer. So usually like a USB or like a CD to get information transferred from the IT network to the OT network. And this almost always requires an insider of some sort, either a knowing insider, like an actively malicious one, or an unknowing insider that you're taking advantage of. Then you want to try and establish a foothold once you're already in the OT network. So if you're trying to take control of the engineering workstation, it's almost always going to be a Windows workstation. That's just usually what ICS engineering workstations run. Obviously, this may not hold true for every system, but it's very, very common. So you can look for legacy Windows exploits. So you can break out Metasploit and see what modules it has for whatever Windows version that workstation is running. You can also look for Active Directory exploits. And then you can also look for vulnerabilities on the protocol level. So like you can look at doing a replay attack like we discussed earlier. It's all going to depend on what you're trying to do and where you can get an initial foothold in the system. Are there any questions on this, or like how you would go about pen testing ICS system? All right. So once we have a foothold, what are some of the things we can do? We can do a lot. It's exciting. Once you have a foothold in the engineering workstation or have access to the PLC, all bets are off. So you can extract that firmware or that ladder logic. You can alter the logic. Oh, I have a typo. You can alter the ladder logic, not latter logic, but ladder. You can start or stop the PLC, and if the company doesn't have any sort of protections against this, this could cause their whole industrial process to come grinding to a halt and cause them to lose millions of dollars. So I'm pretty sure they will not want you to do this in any pen testing assessment that you do. You can also force inputs and outputs, so you can potentially modify the reported state from a sensor. You can also change the input for some component. You can do what's called hot patching. So that means you're applying a change, either a software or firmware change, while the PLC is running. So you're applying a patch live, basically. You can use the SIS to shut down the process. So basically, you're triggering a false positive and causing the SIS to freak out and then say, oh no, the process is unsafe, we need to shut it down. And that will also cause a loss of many, many dollars because the process will come grinding to a halt. You can reprogram the SIS to allow an unsafe state, and that could potentially cause damage to equipment. It could endanger workers. It could cause faulty products to be produced. You can also reprogram the SIS to allow unsafe states and also use the distributed control system to create an unsafe state. So not only are you having the SIS allow unsafe states, you're also directly creating that unsafe state. Whereas the earlier option with reprogramming the SIS to allow unsafe states, you're just changing the SIS to allow it, and then you're waiting for it to happen on its own, which may or may not happen. And then I see what's in the chat. Sorry, give me a moment to check the chat. Okay. All right, continuing on. So I included a list of some tools you can use for pen testing and attack. I'm not going to go through all of these tools, but this is just for your own reference. So feel free to look at these tools later. When I eventually set up the network for you guys to pen test, hopefully you'll get to use some of these tools and put them into practice. Another really useful tool when you're pen testing is Shodan. So it's just a search engine that reports on internet connected devices. So you can find a lot of PLCs on Shodan. So like in the screenshot, you can see all of the reported PLCs running the Niagara Fox protocol, and you see there's almost 20,000 PLCs that Shodan finds just running this one protocol. And most of them are in the United States. So that's scary to know that all of those PLCs are accessible to bots crawling the internet. So you can use this tool on your own to find ICS devices that are open. I would not recommend doing anything beyond that, because then you may be facing legal trouble after that. So you can poke around, see what cool things you can find. Apparently there is a crematorium that you could see on Shodan. So you could actually see an internet connected crematorium on this website because it had some protocol that was connected to the internet. I don't know why. I don't know why a crematorium would ever need to be internet connected, but yeah, playing around with Shodan, you can find some really weird things. So you can have fun with that. So I wanted to list some previous attacks on ICS. It can be an inspiration in your pen testing journey. I'm sure most of you guys have heard about Stuxnet and may know something about it. So I'm not going to really go into much detail. But there's been several notable examples of malware or deliberate attacks on ICS systems. I've kind of listed a couple. The Triton malware is one that was actually leveraged fairly recently. I think that's one of the most recent ones on this list. But basically a unknown state agent was poking around and running this attack framework specifically to refine their malware. They weren't actually trying to take anything down at the time, but they accidentally took down the SIS controllers when they were modifying that application memory, and they alerted, they gave themselves away because of that. And you can actually view the source code of that malware online. It's been posted, and I can send you guys the link if you get really curious about it. You can view the decompiled code, and it's pretty interesting to look through. Then some mitigations and security measures. So we talked a little bit about this, specifically the security alerts, the DMZ and separated networks, and firewalls. Other things that can be done, you can use FPGAs instead of PLCs. So FPGAs are field programmable arrays, and so they are reconfigurable hardware devices where you program them and you're actually reconfiguring the hardware inside of them when you program them. And so they can be used instead of PLCs for like similar controlling of ICS processes. And the reason why you would maybe choose an FPGA over a PLC is because you can incorporate more hardware security measures into an FPGA than you could a PLC, because FPGAs have had a lot more hardware security work done for them. You can also, because they're reconfigurable, you can flash you can flash them with like VHDL or Verilog. You can flash them with that RTL, and it will reconfigure the actual hardware. It's not just whatever you get straight out the factory. So you can actually incorporate like an encryption module or some other hardware protection. You can just program that in versus having to actually redesign the whole PLC. So that's the major benefit of an FPGA over a PLC. Sorry, I'm checking the chat again. Okay, yeah, I can definitely share that link afterwards. I cannot speak to whether it'll put you on a watch list or not. It is on GitHub, so I don't think it will. I think you should be good, but yeah, I can definitely share that malware link with you. Just be careful. I know you should be okay because it's specific to ICS systems, but please don't run it. If you absolutely do want to run it in a VM and make sure there's no network connectivity on that VM. Just treat it like all malware. And then just going back to mitigations and security measures, you can do PLC register indirection. So basically what this means is like if someone were to try and write to a register, it wouldn't write directly to that register. It would kind of redirect. So it would check the value, then it would potentially write somewhere else, or it would not write at all. So it just kind of redirecting the reading and writing to registers. Also, input validation, this should always be done. So just validating that the inputs and the states that you're seeing are what you expect in the given process. And then if they aren't, rejecting those changes. So just reverting back to a known good state. Then hardening those engineering workstations, because those are a big attack vector. Make sure that they don't have glaring vulnerabilities like Eternal Blue or something. Harden them, make sure they're up to date. Then hardware security features. So some PLCs actually have physical switches that change their mode. So they can't actually be programmed or updated while their switch is in a certain position. So you have to physically turn the switch to some sort of edit mode in order to update the firmware or modify any of the PLC's registers or anything like that. So that's really good at defending against pretty much any modifications to the PLC, unless you have an insider threat. And you'll see that almost every mitigation cannot protect against insider threat. Then change management procedures, those also can help mitigate. So anytime the firmware needs to be changed, anytime the topology needs to be changed for the network, like anytime there's a change needed, making sure you have a set process where multiple people have to sign off on it, and that way if a unauthorized change happens, you can easily see, oh, that wasn't supposed to happen, and you can revert it. Then strict access control. So you can whitelist IPs in your OT network, so only certain IPs can communicate with the PLC. The engineering workstation can only communicate with certain IPs. Application whitelisting for the engineering workstation, making sure it doesn't have external applications that aren't trusted and approved. And then just being very strict about what can be on that engineering workstation. Yeah, like email should not be allowed on the engineering workstation. Like phishing should not be something that can impact engineering workstations. But some places don't do that and things happen. And then also you want to monitor your ICS traffic, make sure that the packets exchanged between the PLC and the workstation are what you expect. I also included the names of 2 people who are really active in the ICS field, who are pretty interesting to follow. So Arnaud posts a lot, and he gives a lot of presentations at top name security conferences. So he's kind of the lead in the field for ICS pen testing. He also leads a SANS course for ICS pen testing. So if this talk kind of interested you, you may want to look into his SANS course. Unfortunately, it costs a lot of money, but you could potentially get your future company to pay for it. Then Thiago Alves, he is the creator of OpenPLC, which is a free open source it's a PLC ladder logic editor, runtime environment, and then like HMI creator. So that's like he's done the most work in this space for making it open source, because most companies want to keep it proprietary, want to do security through obscurity, and he is kind of the one pushing back against that and trying to make ICS research available to anyone. And then I have some additional resources for you guys if you want to look more into it. And actually, I have the list for the, I have the link for the Triton malware already included in the slides. So it's this bottom link right here. And now we can kind of get into the exercises. So I'm sorry I went a bit over. So I understand if you have to leave. Which one would you guys want to start with? The ladder logic exercise or the analyzing network captures?
Maybe the ladder logic.
Let me know if you can't hear this video. I won't be able to hear the sound, so I will have to be kind of cognizant of where I should stop based on images. But can you hear that? Or were you able to hear that before I continue?
Yeah.
Yeah. Oh, perfect. Before we actually keep going with the video, for those who wanted to follow along, this does use the Do More PLC software. So you may want to have that up for this. So we're going to kind of follow along with this video and start and stop accordingly.
Programmable logic controllers, or PLCs, are typically used to run factory equipment, and you're probably even wearing or using something right now that was made in a factory controlled by a PLC. And somebody had to program the PLC to make that happen. In this video, we're going to use the PLC to decide which Pinewood Derby car wins the race. Let's assume that the Pinewood Derby track electronics has sensors wired to the PLC that tell us when the cars have crossed the finish line. Now, as soon as the first car crosses the finish line, we want to turn on the light over that car's lane to indicate the winner. So it looks like our PLC needs to watch these two finish line signals, and it needs to output these two light signals. We'll have the finish line wires come into the PLC on inputs X1 and X2, and we'll control the winner lights from the PLC's output terminals Y1 and Y2. Let's also assume there's a reset signal to clear the lights and get us ready for the next race. We'll have that signal come into the PLC on input X0. Now our job as a PLC programmer is to watch these finish line signals, make a decision, and then turn on one of these outputs to indicate the winner of the race, and also to use the reset to clear the lights. PLCs come in lots of different shapes and sizes. We're going to use this Do More PLC from Automation Direct because the software is free and it has a free built-in simulator so we can test our code without having to buy any hardware. If we were going to use a real PLC and not a simulated one, we would set it up like this. First, you get a base. This is a 9-slot base, but you can get them in several different sizes. This is one I just happen to have laying around. Then you select the processor you want. This is the Do More processor that comes with the free software and free simulator. Okay, we need some inputs to read those lane sensors, right? So we grab an input module like this one and plug it into the base. Now, based on that diagram we had a second ago, we wire lane 1 to terminal 1, lane 2 to terminal 2, and our reset button to terminal 0. And we'll also need a wire to supply a reference signal to the sensors. Let's see, we need 2 outputs to turn on the lights, so we add an output module. This one has 16 outputs. We only need 2 of the outputs for this project, 1 for each light we want to turn on. From our diagram, we want to wire light 1 to terminal 1, and light 2 to terminal 2. And again, we'll need a reference signal here for the lights. So again, if we were using a real PLC, that's how we would wire it up. The good news is we don't have to buy and wire up a PLC to try out our program. The Do More software comes with a free simulator which looks like this. Using this, we can test our code for free.
All right, before we continue, if you're gonna follow along with the programming, make sure you get your Do More PLC simulator up and running. So I'm just gonna check on mine. I'm clicking the wrong things. If you haven't downloaded it yet, you can probably just download it right now and it should be done fairly quickly depending on your internet connection. So I think it's about 200 megabytes. Sorry, I didn't realize I hadn't installed it yet, so. So I'll just let it install in the background, but we can continue with the video.
Let's see, it looks like the simulated PLC has 16 inputs, X0 through X15. Again, we're only using X0, 1, and 2, right? And when we click on these buttons, it's just like the track electronics sent us a signal. This X1 input is lane 1, the X2 input is lane 2, and the X0 input is our reset button. The simulated PLC also has 16 outputs, Y0 through Y15. Again, we're only using 2 of them, Y1 and Y2, to turn on the finish line lights. There's a bunch of other stuff here, but we don't need to worry about that for this program. Okay, so let's write our program. Go ahead and launch the software, and you should get a screen something like this. Now we want to start a new project, so we click on New. Let's give it a name. I'm just going to call it PWD for Pinewood Derby. Now you want to make sure you're connected to the Do More simulator, and then say OK. Great, we're ready to start programming. Here we go. PLCs use something called ladder logic because it looks kind of like a ladder. Each line of code is called a rung, like a rung on a ladder. Think of this as the power, and we want to connect that power to drive an output like a light or a motor. In our case, it's the finish line lights. Now right now this power is running directly across this wire to the output. Well, we want to control the output based on our finish line signal, right? So we highlight this block, and we click on this contact right here. And let's give it a name. Let's call that Finish 1. That's the sensor that tells us when the Pinewood Derby car has crossed the finish line. Now the software needs to know which input that's connected to. So click on this guy right here, and let's see, Finish 1 was connected to X1, right? And we say OK. So now when the Pinewood Derby car crosses the finish line, this contact will close and it'll let power flow down to what? Well, we need it to flow to our finish line light, right? So click on that, and we want to set the winner light. So I'll call it winner light number 1 and say OK. The software wants to know what that's connected to, so winner light 1 is connected to what? Y1, exactly. Great, so now when the car crosses the finish line, it'll turn on light 1. Let's do the same thing for lane 2. We need to put a contact here. We'll call that Finish 2. The software says, what input is that connected to? Well, that's connected to X2. And he's going to set the signal at winner light 2. Again, the software wants to know what terminal that's connected to. That's connected to terminal Y2 on our PLC. And we're ready to go. Now, the only problem with this is not really what we want to do, is it? All this is going to do is turn on the light when the car crosses the line, for both of them. We really want only one light to turn on, and we want it to be the light of the winning car, don't we? Okay, well, how do we do that? Let's see, if the car crosses the line and light 2 is not lit yet, he must be the winner, right? Well, that's easy. Click right here and grab this contact right here and put winner light 2 in there. Let's try that. Okay, so what this says is this contact is always closed until winner light 2 goes active. So in other words, when the car crosses the line, it'll close this switch. It'll see this switch is already closed because car 2 hasn't crossed the finish line yet, and it'll light our light. We need to do the same thing down here. If car 2 crosses the line, but light number 1 is not lit, then we need to turn on light number 2. So let's do that. Cursor right here, use this guy. We want winner light number 1 now, and say OK. Well, great, this is exactly what we want. If car 1 crosses the finish line and light number 2 is not lit, then turn on light 1. If car number 2 crosses the finish line and winner 1 is not lit, then turn on light 2. We need to do one more thing. We need to reset these lights when the user presses the reset button. Well, again, come over here, grab a regular contact, and we want the reset line, which we assigned to X0, to reset, that's this guy right here, the 2 lights. We need winner 1. And here's a trick. With the cursor right there, hold down the control key, press the down arrow, and let go of the control key. Now we can add another light here. So we want to reset. Again, that's this guy. Winner light number 2. Well, that's our whole program. This is lane 1. This is lane 2. And then we can reset the winner lights when we're done. This yellow line here says we haven't checked our program yet. So you hit this check mark, and it verifies that everything's great. The green line means we haven't saved it, so I'm just going to save it real quick. And we're ready to go. Now, normally, we would download this to a PLC. We don't have a PLC, so let's bring up our simulator. Click on the simulator button right here. A little dialog comes up telling me about it. Just say OK. Say OK. And it's asking us, what do we want to do? Do we want to go online with this PLC and view our disk project? That's this guy right here. Do we want to go online and view what's currently in the PLC? No, we don't want to do that. Do we want to cancel? So we want this guy. And it's warning us. It's saying, hey, the PLC does not have this program in it yet. Yeah, we know that, so let's continue. And we're ready to go. Here's our simulator right here. Now, there's a lot of stuff here, but we really don't need very much of it. All we need is these 3 inputs right here, X0, 1, and 2, and the 2 outputs, Y1 and Y2, right? Now, this switch right here tells me that the PLC is in stop mode. We need to bump that up to terminal mode so we can program it. To write the program to the PLC, we just hit this button right here. We're going to take this program, hit this button, and that transferred the program down to our PLC. Let's go ahead and run our program by clicking on Run, and we should be ready to go. If the car in lane 1 comes down and trips the finish line sensor, which we know is connected to X1, what happens? Sure enough, the light connected to Y1 lights up. And then when car 2 comes down and trips his sensor, nothing happens. That's exactly right. Okay, let's get rid of those guys. Let's reset our lights. Remember that was X0. And try it again. This time car 2 comes down, he hits his sensor, and sure enough, that light lights up saying car 2 won the race. When car 1 comes down, nothing happens. Perfect, that's exactly what we wanted. So that's all there is to it. We now have a Pinewood Derby track controller that tells us which car won the race.
All right, so I'm cutting the video short a little early, but that pretty much outlines the whole control flow of how to make like a small ladder logic program for a PLC. And that was the example I was going to have us do. But since you guys kind of saw the whole example, we can either come up with a new one, or if you guys would rather just go on to the next exercise, let me know. But yeah, that kind of breaks down ladder logic into a more accessible way like to go about it, because when you're originally looking at it, it's pretty dense. It's not easily accessible, but this example does a really good job of breaking it down. So I don't know if you guys have Do More Designer installed, but you can go ahead and try and create the same program, or you can try and create a different program. So you can try and extend it. You can say, you can add another lane and another car. You can have an additional variable, basically. So not only does it have to cross the finish line, you can say it has to also pass a certain check mark too. And you can modify your program to also accommodate for that. It's basically just whatever you guys want to do to practice ladder logic. So if you are trying to create a new project, remember you want to select that Do More simulator. And in addition to just coils and contacts, you can also see like those math operations that we talked about before. So you can see decrement, increment. It even has linear interpolation. It has random number seeding. It has some file system functionality, which I was not aware of. So it can actually do things using files. But his specific example only used contacts and like output lights. So I'm not gonna walk you through it again unless you want to see it. Is there any desire to have me do that program or a similar program? Or should we move on to the next exercise? Okay. So the next thing, like the next hands-on exercise was analyzing network captures. So you're gonna pull up Wireshark and download that PCAP that I included. It's from the link I sent in the Zoom chat. So just download it from GitHub. So in this ICS PCAP repository, Modbus test data part 1, and download that PCAP. And then load that PCAP into Wireshark by just dragging and dropping. And then you'll get to see how Modbus TCP works. So we can specifically see communication between some engineering workstation and a PLC. So we see some initial communication over TCP. They're negotiating back and forth. And then we can see it switches into Modbus TCP. So if you remember kind of how those packets were formed, it sends a function code and it sends data along with this header, which includes transaction identifiers, protocol identifiers, length, and unit identifiers. So what we always want to kind of focus on is that function code, because that tells us what's going to happen, what we're requesting from the PLC. So whatever this workstation is requesting from the PLC. So it's requesting diagnostics, so it's going into a diagnostics listen-only mode. And then apparently the target failed to respond. But you can see the communication back and forth. This read device identification, this basically returns the product code. Sorry, I'm trying to get down to the more juicy stuff. All right, yeah, so the coils, remember we talked about coils as being representative of only one bit. So this function specifies the read coils function, and it wants to reference, I think, the 10th coil. Or sorry, it wants, yeah, I'm not sure which coil it wants to read. Like I think it, but then you get the response back from the PLC. So the PLC responds back and it says what the value of that coil bit is. So I think it was just requesting the first coil. And then this one, it looks like it's requesting the second one. And then it responds with 0, so that coil is 0. And then it also responds with the third bit, and that bit is 0 because it must be referencing a 2-bit coil, which I didn't realize was a thing. And then this is reading from holding registers. So you can see these are UINT 16 registers. And you can see the register value is 9, and that's from register 5. You can see from from register 6, you can see a value of 24. So this is just showing like kind of the process of querying and then responding back and forth between an engineering workstation and a PLC. You could very easily take one of these packets and then modify the data and then send it back to the PLC, and then you could be doing a replay attack, or you could be doing a man in the middle. So thankfully Wireshark is really nice, and it has this Modbus TCP like interpreter, so you don't have to look at the bits by itself.
Sorry, are you supposed to, or is it just me, or does the screen share not show the actual Wireshark capture?
Oh, it's not showing Wireshark? Okay, yeah. Let me fix that. That's definitely a problem. Thank you for letting me know. All right, there you go. So I will show some of the ones I highlighted earlier. So these are some of the reading and writing operations that we saw. So like this one, it's like the workstation is asking the PLC to respond back with its coil data for the 0th bit. And so it responds back with what that bit value is. So it's saying it's false for that coil. And then for this one, it's actually querying 2 coils at once. So it's referencing, I believe, the 1st and 2nd coil. Or sorry, 2nd and 3rd coil. So what's represented by bit 2 and what's represented by bit 3. And those are also false. And then this is an example of the workstation querying the PLC for holding register values. So it's asking to report the reference or report the value of the 5th holding register. And then the PLC responds back with, oh, hey, the 5th register holds a value of 9. The 6th register holds a value of 24. And those are UINT 16. And then this is what a write operation would look like. So it's telling the PLC, hey, I want to write to a single coil. This is the data I want to write to that coil. This is the coil I want to write to. And then this is a response back indicating that it was successful. So it says for coil number 2, you wanted to write 0 for the data. I'm good with that. Otherwise, it would throw an exception. And it does this, there's the same sequence of writing a single coil. Then there's writing a single register. So it's, once again, asking, hey, can I write to register 5? I want to write hex B to that register. And then the PLC is responding back, all right, sweet. Yep, I got you. For register 5, I'm writing hex B. And then we have some examples of when these functions fail. So this one, the PLC was busy. So it's saying, hey, can't do that. I can't give you back that information. So that's what the exception returned is. It's just saying it was busy. And then this is what happens when unknown function code is used. So I don't know if this is just undocumented or if this is a function code that doesn't exist in the Modbus like protocol. So they're using function code 42, and then they're using this data. So I'm not sure what actually happens here because it doesn't seem like it's throwing a major error. So if you guys find anything out about function code 42, let me know. So that'd be interesting to figure out what it's actually doing there. But yeah, this is just a small sample of what a typical Modbus communication back and forth would look like. if you're curious about other ICS protocols, the same repository where you got this PCAP, they have a bunch of other protocols that you can examine and experiment with. Unfortunately, PLCs are pretty expensive, so most of the time you're going to have to use PLC simulators. And you can experiment with sending Modbus commands back and forth to a PLC simulator, or there's Modbus clients and servers that you can download as software packages. So one I recommend, there's a program called Node-RED. It has a Modbus TCP package that is pretty easy to set up. And if you want any information on that, I can send you that information. So that way you can set up your own little Modbus client and server. So that way you can practice sending stuff back and forth. So I know this wasn't super hands-on with pen testing. I am working on a pen testing environment for you guys that will be a little bit more exciting than the hands-on stuff that you learned today. But the exercises that you saw today will give you a pretty solid foundation for that pen testing environment. So they weren't completely standalone. It'll help you build up the skills for the pen testing environment. So I think that covers everything I wanted to talk about. I'm sorry it went over. If you have any questions about ICS in general, or any specific things from this talk, feel free to shout it out now or reach out to me over Discord or Slack. I'd be happy to talk your ear off about ICS. And I'm always trying to learn more about it. So if there's something you know that I didn't cover, I'd be really interested in hearing it and learning from you as well. So I hope this was an informative talk for you. Please feel free to reach out and give feedback. I always appreciate it. Oh, okay. So Ben, you found stuff on function 43, but nothing on 42. So maybe 42 is completely undocumented. I know when I was doing a little bit more research on Modbus TCP for this talk to make sure I covered things appropriately, they did say there are undocumented function codes. So that may be one of them. We'll definitely have to look more into that. But yeah, that's interesting that there's a function code 43, but nothing on 42, especially when most of those function codes are sequential. All right, does anyone have any questions or anything they want to discuss? All right, I will let you guys go then. Thank you so much for tuning in. I appreciate you guys coming out for this, and hopefully it was helpful and informative.
Oh, it definitely was. Thanks, Claire.
Sure. Thank you so much.
Not a problem. All right, take care, guys.